Good morning, everybody, or good afternoon, I guess, depending on where you are. Um, my name is Mike Rayleigh. I am PAC's Director of Engineering and an acoustician by training. Um, Today's webinar is on acoustical testing, but really kind of doing a deep dive into reading and interpreting test reports. And um, my my intent with this presentation today, this is not an AIA presentation. Um, my intent with this is really to present like an example test report and just talk about test reports and some things that over the years of, first working as an acoustical consultant for 10 years, but then coming to work for manufacturers where I've actually gotten to like oversee acoustical tests, spend time in the test labs. And I've also gotten really heavily involved in ASTM, the standards organization that, creates and sort of maintains the test standards that we use for acoustical tests. So all of my experience and that getting into these long heated discussions about tiny little minute details in these standards, everything that I've gathered from that and how that's kind of shaped how I look at test reports and what I look for in these. And so that's kind of the idea here. So it's going to be a more technical thing. I'm going to kind of go through a test report, look at this. So some of you may be very used to looking at acoustical test reports. For some of you, maybe this is a fairly new thing. So we'll go through that. Like I said, if you've got questions, put them in the Q&A. I've got slides and things like that to go through. I'll probably still kind of go through those, but try and leave a lot of time for questions at the end. But also if there's questions that come up that in the Q&A that seem like good ones, Mike or Steve, feel free to just, interrupt me, and I can kind of touch on those. So yeah, I think with that, I'll go ahead and I'll get into it. So, all right, so reading and interpreting test reports. All right, so just a few kind of things here, the overview of what I'm going to go through. First, I'm going to go through a test report example. This is for a PAC test from one of the acoustical test labs that we use. It's a fairly recent test report, I think maybe from like last year. We'll see the date on it in a minute. And then I'm going to go through that and kind of just like page by page, point out some different things, some things I think, you should pay attention to, look for, some details that are important, and talk about why. And then after that, I have a presentation that is the presentation that I did at NoiseCon this year on the Interlaboratory Study for walls, or for E90, the STC test, specifically for a wall specimen. I'm going to go through that because it talks about kind of how to use test data that you get from a test report and kind of how to think of that in a bigger, broader context. And then time for discussion. So, all right. So here's the test report. So some things to kind of just look for on these, right? So this one is from North Orbit Acoustic Laboratories. There where we do vast majority of our wall testing these days. And let's see, how did I put this together? So, okay. So you'll see the test lab. These reports have a lot of pages to them. Usually, over the years, as we've added more requirements to the standard, more requirements for reporting different things, and we've just gotten, started paying a lot more attention to various construction details and learned more about what construction details make a difference acoustically. I would say that in general, the level of detail that is in our test reports has increased significantly. Like if you look at North Orbit's test reports specifically over the years, their level of detail continues to increase. And if you go to PAC's assembly selector, which maybe Mike or Steve, you guys could throw a link in the chat for that. If you go to our assembly selectors where you can go look at our acoustical test results, you'll see that some of our older reports in there have a lot less detail maybe than the newer reports. So, so with that, one thing you can look at here is a test date. So this one was done just last year, about a year and a half ago. Look at the date. It's important to know like how recent was it, because construction materials change, construction trends change, and also these test standards do also change to some degree. So it's good to know, like, was this done in the last few years? Was this done 20, 30 years ago? If it was done, 20 or 30 years ago, that doesn't mean that it's completely irrelevant. It just means maybe you need to put a little bit more consideration into what may have changed from then until now. I saw somebody's note that like text is not visible readable. It's kind of small. I wanted to kind of put the whole report on here. I will highlight in somewhat bigger text like this box the things that I'm trying to pull out. Hopefully that makes it readable for everybody. Next thing you want to look for is the lab accredited? So accreditation is a whole big long drawn out process. There's a lot that goes into it. Basically what this means is like does this lab have quality control procedures? There are reference specimens that they have to test and show that they get a reasonable result for these. They get audited. I think it's on a yearly basis. If there's any test lab folks on here, let me know. But so there's a lot that go into that. So you want to make sure that if you're looking at test results that it's from an accredited lab. If the lab's not accredited, doesn't necessarily mean you should completely disregard it. You just need a lot more information to understand what exactly you're looking at and how much credit to give it. Lab test reports, labs are accredited. For the most part, if you're doing a field test that's performed by an acoustician, those are not accredited. There are a few labs, few folks that are accredited to do field tests, but that's I'd say very rare. So typically a lab test should be accredited. Field test, you're not going to have an accreditation with it. And then the last thing here just on this cover page is a lot of these will say, the total number of pages, and they'll have some note like this. This might actually be required in the standard. That this page alone is not a complete report. So if you only have a single page or like a couple pages from a test report, and it's kind of obvious just by, a page count or something like that, that some pages are missing, you might be missing some details that are important. And so it's good to have an entire test report. So just some details to look for there. All right, so here in this one, the second page is sort of the summary. So here we have a graph of all of the data. We have the transmission loss data. This is an STC test, so we have transmission loss. We have the deficiencies, a description of the assembly, and a picture of it. So kind of all the information, all the basic information that you need is here on this one page. So this is like if you were going to see just one page pulled out of this test report and presented somewhere, this is probably the page that you would see. But, there's maybe some details that are kind of missing from this. So, so here we have the graph. So this shows you the transmission loss curve. That's kind of the solid, let's see, let me get a little laser pointer here. This solid curve here, right? And then this is the reference STC contour. That's part of how we do the STC calculation. Down here, you can see the deficiencies. So for an STC test, the deficiency is any time that the transmission loss is below the reference contour. It doesn't mean that the wall is like deficient, actually doesn't perform well at that frequency. It just means that it's below the curve at that frequency. That's just how we do the calculation of an STC rating. So this is just nice to kind of see this as an acoustician looking at this. It gives a lot of information. You can quickly see from this picture kind of how well is it doing at low frequencies, how's it doing at high frequencies. Here's this dip. This is a coincidence dip. That's typical sort of behavior of drywall. You can see these kinds of things. Just helpful information to see. Here you will see the transmission loss data. So an STC rating only really is calculated based off of the transmission loss values from 125 to 4,000 hertz. But here they present additional data because especially this low frequency data is helpful. So not part of the STC calculation, but it's helpful data. Also, if you go back and you look at older test reports, you'll tend to see them limited more to just that 125 to 4,000 hertz range. I think over the years, we've put more and more emphasis on low frequency information, and so you'll see that included in more test reports. So another advantage to looking at probably more recent test reports is you might get just additional information that's helpful. Here again, you see the deficiencies just shown in a table rather than on the graph, so you can clearly see what these are. Here's the description of the assembly. And this one's a pretty detailed description. So, it calls out specific, brand and type of drywall. It also calls out the specific screws, the size of the screws, and the screw spacing, which that's an important thing. I'll touch on that a bit more later. You'll see the framing. We have it in both, these are steel studs. We have both the gauge and the mill thickness. So I've done other presentations on steel studs and the effect of mill thickness and all of these kinds of things and stud gauge. So if you want a deeper dive into that, you can go check out those presentations. But just generally speaking, the stiffer the stud, so the thicker the steel, the more sound that it transmits and the lower acoustical performance that you tend to get, all other things being equal. Again, older reports, older versions of like the Gypsum Association Fire and Sound Design Manual would often just list steel studs as steel studs without any sort of reference to gauge or mill thickness. So gauge is the way we still, a lot of us still tend to talk about stud like metal thickness, but the actual steel framing industry moved to using mill thickness quite some time ago. I think like a decade or 2 decades ago. Just the rest of the world really hasn't like caught up to that. It's important though to talk about mill thickness instead of gauge because over that time we've also moved towards using sort of equivalent gauge studs where they use a thinner steel, but that steel is maybe a stronger steel, has a higher yield strength, and maybe it's shaped in certain ways that also increase its strength when it's formed into a stud shape. And so this is like a true 25 gauge steel stud at 18 mils, but a 25 gauge EQ might be 15 mils, and that different mill thickness and things can affect your acoustical results as well. So if you're looking at tests for steel studs, any kind of steel framing, it's really important to pay attention to the gauge and ideally really the mill thickness. So that's an important detail on a test report. If you don't find that, then you gotta kind of take that one with extra grain of salt because there's a lot of variability that you can't really account for in that test report. And I realized actually here I'm talking about, this is the hat channels. Down here is the actual steel studs, which is in this case was 54 mil 16 gauge. So this is a heavy structural steel stud. You've got your insulation and then your other gypsum board layers. So there's a lot of information in here. Here's a nice little schematic. So it's easy to just kind of picture the wall. A lot of test reports don't have this, but it's nice to have it in there. So yeah, a lot of details there in it. Oh, and Jerry says NavLab assesses each lab every 2 years. So Jerry was a NavLab assessor, so you can take that one to the bank. So it's every 2 years they come. NavLab is the primary accreditor there through NIST. But then there are other ones, like A2LA is another accrediting body, and they have these kind of like reciprocal agreements for accreditation that's like then through NavLab or into NIST or something like that. But basically you want to just kind of look for this accreditation and they actually list their certificate number here too. So, all right, there's your schematic of the wall. Okay, so here's a section, and I know the text is small. Again, I'll highlight some things and just kind of talk about them. But this describes more the approach, like the actual installation, the test methods that were used, and some different things. So you have a little bit more details about what they did for this actual test, which is really helpful. So on the installation, they tell you when it was built. Sometimes you'll look at a test report that has maybe a more recent date, but it's a reissue of an older test. And so if they have information in there about when the assembly was actually constructed, that's really what matters in terms of like the materials that were used and things like that. So that's a helpful piece of information in there. And then the test methods, here they list the standards and the versions of the standards that were used. So this bit here, E90, that's the actual test standard. And then after this, the 23, that's the year version of it. So this was done in 24, they used 23, which was the most recent version at that time. So again, these standards, there have been some changes to them over the years. There are a bunch of changes happening to them right now. We're working on a bunch of standards at ASTM and making a lot of changes to a lot of standards. Not all of them really substantive changes, but there are some things like in some of the field measurements, we're changing how you do the background sound level correction. That could slightly change your results, changing some of the reporting requirements and these different things. So it's important to kind of get some idea of what version of the standard was used, and just it's a good quality check. Like, is the lab using the most recent version of the standard? And then E413 is just the classification for actually calculating the SDC value from the TL values. So here's a statement. I think this statement is required by E90. It says all results reported herein were derived from tests performed in full accordance with test method ASTM E90. The laboratory measurement system fully meet all requirements of the test standard, so on and so forth. All values stated are derived from single direction transmission loss measurements. So there's a number of different things in here. So you can deviate from what's required in the test standard. And in some instances, there may be good reason to do that. Maybe it's just a weird test assembly, or you're going for, you're trying to capture some other kind of information about performance that's not really well captured by the exact test standard as it's set out. And so you might choose to change things up in one way or another. Depending on how much you deviate from that and things, you can still call it, an ASTM E90 test report, but you are supposed to call out any things where you deviated from the test standard. You're supposed to say, like, we did everything according to the standard except for this or these couple things, and explain what those are. So it's apparent to everybody what those deviations are, right? Just transparency. And then the laboratory measurement system fully meet all requirements of the test standard. And the annex, which is for qualification, that's all really wrapped up into sort of the accreditation. Like, as part of your accreditation, you're supposed to meet those requirements and these kinds of things. And then the single direction transmission loss, you can measure transmission loss both directions, and you should get roughly the same answer. Reciprocity would say that you should get the exact same answer, but just differences in room sizes and flanking paths and things like that, and just the inherent variability in the test, you can get some slight variations just between one direction and the other direction. We've done 2-direction tests at North Orbit, and the results are really, really close. Though there is, still some random variation in there. Typically would just do single direction transmission loss tests because that's sufficient, and doing tests both ways takes more time, costs more money. There are some labs, National Research Council of Canada is one that I think often does the test in both directions. So just interesting little tidbit. So here's one. The standard deviation of reproducibility is stated in ASTM E90 as less than 2 dB for these frequencies. Detailed test procedures for this test method, the flanking limit report, repeatability measurements, and reference specimen tests are available upon request. So that's also required within the standard, that the labs are supposed to have all of that stuff available upon request. So if you're really interested, and I, as a manufacturer that's like paying to go do testing at these labs, am really interested in these things, this is all helpful information to have. The flanking limits are especially important, and I don't have it here in my presentation actually, but I'll pull up another test report. On wall assemblies, especially at North Orbit, North Orbit has a really high flanking limit. I think it's in the mid to high 80s, maybe even higher than that. So we rarely run into flanking limits at North Orbit, though we do have a whole test series where we kept hitting the flanking limit. The floor ceiling labs tend to have much lower flanking limits, somewhere in the like mid SDC 60 range for airborne sound isolation. So the majority of the floor ceiling tests that we have, and that many others have as well, are sort of bumping up against those flanking limits for airborne sound isolation in a floor ceiling test. And you'll see, I'll point this out later, in the more detailed data reports, there will be these little flags, and there should be flags for anything that was maybe flanking limited. So that's a really important thing to go look for. This reproducibility is sort of the expected variation between labs when you test nominally the same specimen. The next bit of this presentation is going to be on the E90 round robin that I helped run, and I'll talk a lot more about that there. That number is going to change as soon as we get the precision and bias statement ballot actually passed through ASTM. So, all right, here's specimen description. So this is a much more detailed bit of the specimen. So just some things here. Description of the framing, like when the framing was actually constructed. Again, mill thickness, stud gauge. Also sort of how it was installed into the opening and how it was sealed here. So you see the perimeter of the frame was sealed at the specimen opening with non-hardening acoustical sealant. So seals can make a difference. Boundary conditions, just how you mount this thing into the frame can make a difference. So having, you know, some clear transparency on all of these different kind of construction details is really helpful to understand what's going on in this test. And if you're trying to kind of compare between two tests and see like, okay, why is this one different from this one? It might not just be the actual construction of the specimen. It might be some of these other things, like what lab it was tested at, how it was installed in the opening, how it was sealed, all of these other things. So having more of these details helps us better understand and look for potential differences between tests. Sheathing. So this is the drywall. One thing I want to point out here is the spacing of the screws, 12 inches on center. So screw spacing, especially when you've got direct attached drywall, the screw spacing can make a difference in the acoustical results. This is especially true for like constrained layer damped drywall. And so you want to make sure that the screw spacing that was used for the test is in line with the screw spacing that you're actually going to use in the real world. Typically, wider screw spacing will get better acoustical results. Tighter screw spacing will get lower acoustical results in those assemblies where screw spacing affects things. Screw spacing is also dictated in UL fire designs. So if you have a UL fire design that requires a maximum 12-inch on center screw spacing, but you've got an acoustical test with 16-inch on center screw spacing, that acoustical test isn't entirely representative of what you're actually going to get in the field. And if you're, you know, trying to scrape by a couple STC points to get to your STC 50 code minimum or whatever your target is for that project, that screw spacing might be enough to kind of nudge you one way or the other over that boundary. And when you include that plus all the other sort of sources of variation and things like that, it's just one more detail to pay attention to, and you want to kind of make sure everything's lined up in your favor so you're as likely as possible to get the results that you want in the field with the real construction. All right. And then here's more about the kind of the installation and seals, shims, and then the perimeter of both sides was sealed with 2-inch wide polypropylene tape and 7/8 dense putty tape. And this is pretty common in assemblies that we seal the perimeter of them into sort of the test opening with some sort of like dense putty, because we're trying to test the sound transmission through the partition, the primary partition itself. We're not really trying to test the gaps or, you know, leaks, how good our acoustical sealant is when we're testing a wall partition. So we do extra stuff to seal those gaps. So just kind of keep that in mind, that like those, you know, seals and those kinds of things are not really sort of included in these. We've gone above and beyond what's actually going to show up in the field because we're just trying to test sort of the middle of it, not that perimeter. Same thing for a fire test. They have these big seals at the perimeter of an assembly for a fire test. So you're really just testing how long it takes the fire to burn through the primary bit of the assembly. There are kind of other ways that you can test sealants and things like that too. All right. Specimen description. Here they've got a bunch more details on like all of the panels and things like that. Like you see, there's just a ton of details in this test report. So kind of thing you're not always going to dig into. But if you're, again, trying to make comparisons between two different things, these details can be important in those comparisons. So it's nice to have them here when you need them. Here, the big thing really to kind of call out is surface density. So mass makes a difference in sound transmission, right? And so if you can see this, if you're comparing between two test reports, you might see that one maybe got a slightly lower rating than another one. And you might go look at that and see, oh, this drywall was only, you know, 2.1 pounds or so, like that, pounds per square foot. This one was like 2.4. Well, the heavier drywall might tend to get a better result. And like if you look in our database for wall tests, we'll have some wall tests, with RISA clips with type X drywall and some with type C. Well, type X tends to weigh around 2.2 pounds per square foot, although this Pabco gypsum is on the lighter side, it's 2.08. Type C drywall tends to weigh 2.4 pounds per square foot. So you'll see a little bit better performance out of type C versus type X. So that could, again, explain some slight differences between tests. I see somebody says, can you comment on standard E336 for institute testing? Yeah, I can touch on that in a little bit. Here again, we have the framing, a whole bunch of details, the dimensions of these steel studs, the metal thickness in terms of gauge and mill thickness, the number of studs, all of these kinds of things. So lots of good details here. Here we just have an image. Again, this shows the actual like clip layout. One thing that I think is really nice, like if in an ideal world, there would be enough information in a test report so that you could go back and recreate that test as identically as possible. And so see if you get the same result, right? Like that's good science. You don't just get a result once, but you try and recreate it, right? And so if there's enough detail in the test report where you're like, yeah, I could go rebuild that, go redo that exact test and like match all of the material parameters and properties, match the construction exactly. That's all really helpful. That's a well-documented test report. Chamber volume. And I think we're almost to the end of this this bit here. Yeah, page 7 of 8. So here, the chamber volume, you can see that the source room is 217 cubic meters. The receiving room is 349. Larger chambers, you can get better, it's kind of a judgment term, but you can get better measurements at lower frequencies. So if, this is really for the acousticians on here, like if you're looking at a test report and you see a very small chamber volume, think about the modal density of that. And if you're looking at data down to 50 hertz, if you've got a really small room, think about like how much stock you should really put in those low frequency measurements down to 50 hertz, where you've got very, very low modal density in that space. So just another thing to consider, if you're trying to, design something for low frequency sound isolation and you're comparing, this assembly from lab A to this assembly from lab B, well, if lab A has a receiving room volume of 80 cubic meters and lab B has a receiving room volume of 349 cubic meters, I would be very careful about comparing low frequency data between those two labs because of the dramatically different volumes of those two labs. All right, so here, I don't think I meant for that to come up first on the bottom. So this is the sort of extended data. So here they've presented the transmission loss to a 1/10 of a dB instead of as an integer. You have data flags. Man. So the flag is down here. It's buried. I apologize. I got my animation sequencing off. So there are data flags, and there are a couple different ones. I think there's 3 different ones in the standard for E90. So one is if the transmission loss was affected by background sound. So for this test, right, you have 2 rooms. You have your source room and your receiving room, and you have your specimen, in this case a wall, in between them. In the source room, you make a bunch of noise, you measure how loud it is, and then in the receiving room, you measure how loud it is in there. You take the difference, and then you do some other maths, and that's how you kind of get your transmission loss, which is the reduction in noise from one side to the other, and then you get, from that, you get an SDC rating. So if your partition blocks a lot of the sound, and so what's in the receiving room is pretty quiet, it might be quiet enough, the transmitted sound through the partition might be quiet enough that it's close to just the background sound level in that room without the noise source on. And so it then becomes hard to distinguish what is the sound coming from the source room, from the noise over here, and what's the sound that's just in that room already, often coming from like exterior noise sources. And so if those are too close together, we don't have a good enough signal to noise ratio, and we can't really distinguish what's coming from the partition. So that limits our measurement of the transmission loss, right? So you'll see a flag for that. And then another flag that you'll see is for the flanking limit. So flanking sound is sound that moves, that is transmitted by some means other than through the specimen that we're trying to test. So it could be through the lab wall that's surrounding the specimen. It could be through the other walls, through the floor, through the ceiling, all of these other potential paths that the sound can go around. And so, you know, the labs are built so that they provide a lot of sound isolation through all those paths, so that sound that you're measuring should just be what's coming through the partition. But if you build a really high performing partition in there that starts to perform as well as the rest of the lab, then you get, you know, you start to get more sound transmission coming through the rest of the lab that's contributing to what's in that receiving space. And so again, it's hard to differentiate what's being transmitted through the rest of the lab and what's being transmitted through the partition that you're testing. And so the labs, as we saw before, are supposed to establish their flanking limits. That's a whole long discussion of how exactly you should do that. But the labs are supposed to establish their flanking limits and then be monitoring, you know, your measured transmission loss values and see if they're getting close to those flanking limits. And if they are, if they're within 10 dB, I think it is, then you're supposed to put a flag here, say this might be flanking limited, like, which means that the transmission loss value might actually be higher than is reported. We just couldn't measure any higher, right? And then the last one is a filler wall correction. So in at North Orbit, their opening where they build the wall and put it in to test it is, is it 8 by 12 or 10 by 12? I can't remember. Let's say it's 8 by 12. But say you want to get an STC rating for a window that's like 2 foot by 4 foot. Well, you've got an 8 by 12 opening, you've got a 2 foot by 4 foot thing that you want to test. How do you do that? So what you'll do is you'll build a filler wall, something in that opening that should be a really high performance wall. And then within that, you'll create a smaller opening. That's where you put your window. And so then the lab needs to determine what the transmission loss value is of that filler wall. Because if you've got a really good window that starts to approach the transmission loss of your filler wall, again, you're going to get sound through the window, but also through the filler. And that's going to make it harder to figure out what's just coming through the window. So in that case, you would have a flag for a filler wall correction. So in the stuff that like PAC does, where we're building whole walls, typically we're occupying the entire opening. So either for a wall or a floor ceiling assembly. So you really shouldn't see flags for filler wall corrections. In ours, most of the time, there are maybe some particular labs where they've kind of just usually shrunk down their maximum opening size or something like that. So you might see that show up, but the filler wall correction is going to be a lot more common with, you know, doors, windows, those kinds of things that tend to be much smaller sizes. All right, and then I think, yeah, so here's the flanking limit. So in this case, I don't think it's actually required by the standard right now to be reported. I think that's something I'm actually like pushing to have us change in E90. But North Orbit reports it, so you can very easily compare your transmission loss values over here to your flanking limit and see how close you really are. So then the last thing on here is this 95% confidence interval, and I just want to see, like, in the chat, who actually knows? Anybody want to give a guess of what this 95% confidence interval is? And Jerry, I'm glad you're here, because I don't want to get too deep into this, but I think it's important to point out what this is and what it actually means. So yeah, if anybody's got a guess and wants to throw it in the chat, throw in what you think this 95% confidence interval is, and then I'll do my best to give a rough description of my understanding of what it is, and then Jerry, if I go off track, raise your hand and jump in. Any takers? All right, nobody wants to guess. Okay, so I see 95% of the time the real value will be plus or minus x dB from the indicated value. Yeah. So kind of, and the exact wording of like just statistically what it means is already a bit tricky, and I've read it and heard it explained a number of different ways. But oh yeah, here's Kevin, my statistics buddy. But what does that interval represent? What data is it actually tied to? That's the thing, right? And so when I used to look at these test reports as an acoustical consultant, I used to think that that was the 95% confidence interval for the transmission loss result for this test. That's not the case. So as best I can understand this from rereading the standard again last night, which like changed my understanding a bit again of what these are. You can see here in this note, it says composite 95% confidence intervals from room qualification testing. So that's the room qualification testing that we saw some notes about before that like this lab has done. They've met the qualifications within E90. Extended frequency results below 80 hertz and above 5,000 hertz are for reference only, right? Specimen TL rounded, blah, blah, blah. So really this composite 95% confidence intervals from room qualification testing. So they're not from this actual test at all. So they're not tied to these transmission loss values. And I went back and I looked at the E90 standard last night. And I think what it is basically you're supposed to take sort of a reference specimen. It doesn't have to be the actual ASTM reference specimen, but it's supposed to be a specimen with a SDC rating, I think, between 25 and 50. You're supposed to put that in your opening and then basically run an SDC, an E90 test. And you're supposed to look at the standard deviation between fixed microphone positions in the source room and the receiving room, and then also for your absorption that you measure. And so when you do these tests, one of the ways that you can do it is you, like in your source room, you have some speakers that make a bunch of noise. It sounds kind of like TV static. And then you want to sort of sample the sound that's in that room. So you get kind of the average sound that's in that space. And so you'll use different microphones at different locations to kind of sample the sound in the space because it'll vary somewhat within the space. Typically, you'll use probably like 5 or 6 different microphones at different locations. And so you're looking at the difference in the sound level between those different microphone positions. And so you're really looking for a uniform sound field. So in an ideal world, you get the same sound level at all of the different microphones. But we don't live in an ideal world, so you'll have some variation in sound levels between those microphones. But we want to minimize that variation, right? And you'll do that in the source room and in the receiving room. And then you'll also measure the reverberation time. And there's only one value for reverberation time. Maybe it's the receiving room. I don't remember. But you'll look at the difference in the reverberation time between all of those microphone locations. And that's supposed to be, when you add all of those variations up, it's supposed to be below some number. If it's not, then you add more microphones and like do the process again until you kind of get this and figure this out. This is kind of part of your room qualification thing. But so it's for one particular specimen that you tested like one time, and maybe you have to do this multiple times, but it's not at all directly related. It's somewhat related, but it's not the expected variation in the transmission loss values that are in this report. And so a conversation at ASTM is actually removing the reporting of this 95% confidence interval, sort of separating it from the presentation of the actual TL results, because it's not directly related to those. And the way I used to look at this would be like, okay, here's my 95% confidence interval. It's plus or minus 1.6. So I'm looking at a range of like 33.6 to 36.8 for the TL at 100 hertz. That's not true. So I think that's an important thing to understand, that this is not the uncertainty values for this. This is not sort of your error bars for your TL. Yeah, so I see Dave says, so this is the confidence interval for the test setup, not the confidence interval for the test sample. The only way this could be the confidence interval for the test sample variation is by testing numerous samples. Yes, so you would have to test multiple samples, like multiple, builds of the exact same specimen and see what that variation is. And then you start to get that sort of build variation. I will go into that more, I think, when I do my next bit and I talk about the round robins a little bit. And I realized I spent a lot more time on this than I thought. So Jerry says, "Good job." Whew, okay, I didn't mess anything. Jerry. I'm glad you're here to keep me on track with this. So, um, any questions? I did a big deep dive into this. I will just open it up to questions now because I realize I spent more time talking about this than I kind of expected. So let's just open it up to discussion. I have other slides here on the round robin. I may just kind of go and do another presentation on that so I can spend a lot more time talking about that because I imagine that will have a lot of questions. So yeah, anybody got questions, want to chime in?
Hey, Mike, we had 2 questions in the Q&A. One came
Sure.
from John Creighton, and he asked, please elaborate on flanking limits. And I think you already touched on some of the things that John might be interested in, but maybe talk about the differences between flanking limits from lab to lab and how that might factor into, say, the test of a similar or same specimen in each lab. I don't know.
Yeah, let me that's a great question. So let me pull up another, I'm going to pull up an ADM assembly here where let me just pull up a test report so that I can show one that has, yeah, here we go. Okay, so let me zoom in on this. So I'll scroll to the top so you can see the assembly while I talk. So, okay, so flanking limits, how do I explain this? So you're trying to measure the sound that's just coming through this opening, right? So you have for a floor ceiling test, and I wish I had like a better visual for this. For a floor ceiling test, or sorry, for a let's say for a floor ceiling test, because that's what I have up, right? So you have basically two big boxes, one stacked on top of the other, right? And you make noise in one and you measure the noise in the other one. Well, I guess you measure it in both and you're trying to figure out the difference between them, right? And that's how much noise the assembly is reducing in the transmission. So the way we tend to do it in our labs here in the US is we have these really big boxes. We try to get bigger and bigger boxes so we can measure lower and lower frequencies. So you have this big box, and let's say your floor in the room is 20 by 20. Those aren't good. You shouldn't have them be the same dimension, but just let's say it's a 20 by 20 square. We're not building a 20 by 20 floor ceiling assembly to test. We might build a 10-foot by 12-foot floor ceiling assembly to test. So it's this hole in the middle of this much larger floor that is the lab. And you've got a 20 by 20 floor in your source room and a 20 by 20 ceiling in your receiving room. So you've got this, right? And then just a little hole in between them where you actually put your test specimen. So you're going to get sound transmission through your test specimen, but you're also going to get sound transmission through the floor and ceiling that's all the way around them. So ideally, the lab is designed so that you get very, very, very little sound transmission through the rest of the lab, and all the sound that you're measuring in the space below is through just the thing that you're testing. Well, in reality, it's really hard to build these things for these labs that don't let that much sound through. And also, as we're trying to push the level of sound isolation that we can get from our partition, right? The things that we're trying to test keep getting better and better and get closer and closer to the sound isolation of just the lab ceiling assembly itself. And so then what you do is you go in and measure, and like if you just stand in the room down below and you're listening and you're looking up at the assembly in the the opening up above, you're like, I mean, it's in a reverberation chamber, so it's hard to tell where the sound is coming from anyways. But you're like, I can't tell where the sound is coming from. It's either coming from our specimen or it's coming from the rest of the lab. It might be coming from the lab walls. It might be from the lab ceiling, maybe our specimen, kind of all of the above. And even if you get up close to all of them and you like kind of put your ear to it, you're like, I hear some from the walls, I hear some from the lab ceiling, I hear some from my specimen. And so like the sound's coming from all these different places. So you can't say that it's just coming from the specimen you're trying to test. And so that's where you get into these flanking limits. You just can't tell what's coming through the thing you want to identify. And so that means we can't, we reach this upper limit of what the transmission loss values are that we can measure in a space. So here we have this test. We have a whole bunch of these different tests on our database. 8-inch concrete slab. It's got some tile and a rubber underlayment. And then this version of the RISC 1 with a little clip that you can shoot into it. This is not drawn to scale. This is a 3 3/8 inch airspace. I just, probably for obvious reasons, wanted to make the pack product look a little bigger so it stood out. But little airspace and then a layer of drywall. So STC63, but if you dig down into the test report, here's a Intertech floor ceiling test report. Also a lot of information about material source installation, instrumentation, lots of details in this too, right? Test procedure, blah, blah, blah. Detailed assembly description, a lot of the same kind of things we saw in the wall report too, right? So here we get to the test results for airborne sound transmission losses, right? This is STC Rosetta. So here's the specimen TL. Down here, you'll see this note. Specimen TL levels listed in red are potentially limited by the laboratory flanking limit. And you'll see that all of them, except for this one, is blue, which says the lower limit of the transmission loss. I think that's also supposed to be a flanking flag. But all of these are limited. So these are not the actual transmission loss values of the specimen. They're just roughly the highest values that the lab could measure. So the actual TL values might be higher. If we went and measured this in a lab with a much higher flanking limit, we might get higher transmission loss values, and we might get a higher STC rating as well. So that's an issue. And like this lab, Intertech, like not to pick on them, like this is common, and their flanking limit is similar to most of the floor ceiling labs. Maxon has a higher limit, and NRC has a significantly higher limit. But I think Intertech York stated like STC flanking limit is about STC 64 or 65. So if you're within 10 dB of the TL, the flanking limits, you flag it, right? So anything from like an STC 55 and above might start sort of getting affected by flanking. And I see a lot of acousticians and folks that are recommending, STC 65, STC 70, maybe even higher for floor ceiling assemblies. Like the only place I can go measure that is NRC. And they are really slow and really expensive. They're a government research lab. They're just not intended to be a high throughput commercial lab. So we're really limited in our ability to actually just go test and get information for those high performance assemblies. Hopefully that answered your question and then some, John. Okay, I see the other question. What is the effect of stud stiffness at the low frequencies? If we are most concerned with sub 125 hertz performance, do stiffer studs help at some of these lower frequencies? Great question. I would say that depends somewhat, and you should go check out. We have another webinar on steel studs. This is on our webinars page. If you come up here to media webinar videos, there's one on steel studs. This one, I think, simplify steel stud design with the RISC 1 and Pabco gypsum. That one I had Ben Schaefer, who's the acoustician for Pabco gypsum Quiet Rock. He's done a ton of steel stud testing on a bunch of different steel stud gauges and things like this. And in there, I think he and I present data from a lot of his testing that looks at sort of the effect of mill thickness and stud spacing, both ways that you can change the stiffness of your overall wall, and the effect of that on the full frequency range. So yeah, I would say there's more information than that. You got to be tricky because if you get stiffer, like it'll tend to transmit more sound through, but if you've got good isolation, then you won't get that increase in transmission. But then your isolation is much less stiff, so that maybe sort of affects the overall stiffness of your panel, and you might sort of lose the intended benefits of that additional stiffness. So it gets complicated. But if you have some specific situation or you want to do a deeper dive into that data, I would say go check out that presentation. And then if you still have questions, feel free to just reach out to me directly. I'm happy to kind of dive into it and see how I can help.
Mike, Dave, on your question, I put in the link to our steel stud brochure that has some graphs on it that might help that a little bit.
And I just saw somebody's question pop up that says, are these available on YouTube? So these are all on YouTube.
Yeah.
And Steve or Mike, maybe one of y'all can put the YouTube link, but there's also, since I'm right here, I'll just go throw this in the chat. And there they are on our website. Oh yeah, Gerald had also said, can you comment on standard E336 for in situ testing of attenuation between rooms and buildings? Sure, Gerald. Do you have any more specifics that you want on that? I'll just, if you want to, somebody wants to unmute Gerald, or if you want to add some more in the chat, go for it. E336 is the, just for some context for everybody, E336 is the ASTM standard for doing airborne sound isolation in the field, whereas E90, the one I've been talking about, is the standard for doing it in the lab. Okay, nothing in particular. So in the field, there are a number of different metrics that you can get. So there's ASTC, there's NNIC, and NIC. And basically you measure them all about the same way, and you measure them, and that's similar to how you do an E90, an STC test too. So you make noise in one room, measure how loud it is in there, and then go measure in the other room on the other side of the partition that you're trying to test, measure how loud it is in there, take the difference, and then do some kind of math according to the standard. The big difference in a field test is that, like, you're in the field, you're in the actual building, and you haven't gone to all of this effort to isolate everything else so that you're just testing the sound that's coming through your partition. You have all of these other paths, and they're just normal building construction, not, high-end, very specific laboratory construction. So you're going to get a lot of flanking sound through all of these other paths, right? And so you're not just measuring the sound transmission through the wall between the units, but all of these other potential paths too. There's the three different metrics. There's differences in, do they account for sort of the absorption or the reverberation time in the rooms? Because if you have a really lively space with just a bunch of hard surfaces, very little acoustical absorption, your sound levels in that space will tend to be louder. Whereas if you have a bunch of soft surfaces that will absorb a lot of sound, your sound levels will tend to be lower. And so the ASTC and NNIC measurements try to sort of like normalize for that absorption or reverberation time and kind of adjust it to a norm. The NIC measurement doesn't do that. It's just, here's what you got. And there's some other sort of more nuanced differences in terms of exactly how you do the measurements, what sound you're trying to capture, and room volume restrictions and all of these other things. So yeah, that's kind of the main gist of that, I think. Yeah, anything else? If there's no other questions, I would just say that just in general, as I have like gotten into these, the details matter, and the more I learn about the ASTM test standards and construction and the construction and material variables that affect acoustical performance, the more I think a lot of these details matter, and often the more complex it becomes to figure out when a detail matters and when it doesn't matter. So it's really nice to have all of those details available. Of course, then it means there's more details that you've got to think about and try and like sort through and figure out, does this one matter? Does this one matter? But it's nice to have them so that you can at least go through that thought process. And so for acousticians, I would say I really highly encourage you to dig into these test reports and really look at these things in more detail and really pay attention to the information that's being presented to you. I think it helps you do better work, and then it also helps you ask better questions of the manufacturers and the test labs. Like, I'm happy to get questions from acousticians. They're like, hey, Mike, like, there's this detail in your test report, and like, this thing doesn't quite make sense. Or like, you have this drawing of an assembly and it has this detail, but the test report says this detail. Like, I'm happy to get that, because that means like you're really paying attention and like you're engaged, and then we can have a good conversation, and probably we both learn something at the end of that conversation. If you're an architect, like, you know, you're probably not going to be digging into the flanking limits and the 95% confidence intervals. Hire an acoustician so that they can do that. But just be aware that this information is out there, and this is the level of sort of like detail and documentation that can and should be provided. And so if you're not getting this, like, try to get it. And if you can't, like, maybe go look for other places where you can get that level of documentation so that you can really adequately evaluate the products that you're putting into a project, and in part staking your reputation on. So with that, unless there's any other questions, I think we'll wrap it up. I see one more. Gerald says, has a webinar been done on in situ testing? No, I might do one, but I would say that I would have to bring in some friends probably to do that presentation. And I have the folks in mind. They're the two ones involved in completely rewriting and reworking E336 and E1007, the two main like field test standards. There's a lot of stuff to those test standards, and I've really been focusing on laboratory testing. And so even though I feel like I've learned a lot about the field tests, I don't think that I know them well. But there's a lot to dig into in those. And so, Gerald, if you've got particular questions about those or something, like, feel free to reach out to me. Oh, somewhere in here, I have at the very bottom of this. Here's my email and just the main pack email. So if you've got any questions or anything like that, feel free to shoot me an email. Yeah, Gerald, if you or if anybody else here has particular questions on field tests or anything else that I covered or didn't cover, shoot me an email. I'm happy to have a discussion, and always happy to get good ideas for other webinars too.